Hello, geometry students. It's transformations day 2. We're going to do a little bit more with reflections, and then we're going to move on to talk about translations. So I have pre-drawn all of the diagrams that they hand you. If you want to do that in one shot, feel free. Otherwise, just pause the video if needed to be able to get all the diagrams drawn in. All right. So first thing that we actually talk about is a little vocab. So it's saying an isometry. It's a transformation that does not change the blank or the blank of the original figure. And what that is, it is the size or the shape. So it shouldn't be distorted in any way, shape, or form. All right. Another name for an isometry is called a rigid motion. And in those multiple choice questions that you had in yesterday's notes, you saw that terminology being used. So when it says, is a line reflection a rigid motion? Explain. Well, if we can kind of visualize a little line reflection, pretend we've got a little, triangle ABC over here. If we take and flip it over that line, C would end up here, A would end up here, and B would end up top. Now, my drawing is not the best, but what you should have is the same triangle, just flipped over in location. So it's still the same size. It's still the same shape. So absolutely. So the explanation, we can say that the pre-image, which is triangle ABC in my little example, is the same shape and size as the image, which is the answer, triangle A prime, B prime, C prime. Or you could say it the other way around. You could say the image is the same size and shape as the pre-image. Either way. All right. For those of you that like some rules, let's write them down. Maybe use this as a chance to kind of test yourself. So reflecting over the x-axis. Here it means the x stays the same. Y is going to switch. When you reflect over the y-axis, now it's the reverse. The y stays the same, and the x gets negated. As for the origin, here they both get negated. And then the last one, when you flip over the line y equals x, literally the y and x switch spots. So it becomes y comma x, like that. So let's talk about doing some practice with applying them. So the first one here, it says the vertices of triangle ABC, points 1, 5, 4, 9, and 5, 4. So I have all of mine here, are given. Draw triangle A prime, B prime, C prime, which is the image of triangle ABC, after a reflection over the line y equals x. So a reflection over the line y equals x. Again, that's that perfect diagonal line. So that starts at 0, 0, and then it goes through 1, 1, 2, 2, 3, 3, and so on. So I'm going to draw mine in. I probably should have drawn it in pen or pencil first and then gone over it, but that's okay. Maybe I'll add that in underneath just to make sure that you can see it. See it well. There we go. Okay. State the coordinates of the image. All right, so each one, let's apply the rule. So A goes from 1, 5. A prime, we are flip-flopping. So 5, 1. So over here at 5, 1, there's A prime. For B, we are starting at 4, 9, and we're going to land at 9, 4. And I think it does help. You guys, you do not have to label all the graph. Excuse me, but just for your own reference so that you don't lose track of where you are. I do think that it can be helpful here. So it went from 4, 9 across to 9, 4. And then C, starting at 5, 4. C prime should then be at 4, 5. So what you will notice, whatever side of the line it started on, it should flip to be on the other side of the line now. If having the diagrams overlap is a little confusing, sometimes choosing a different color can be helpful. So if you have some colored pencils laying around, or even pen versus pencil, sometimes that kind of helps distinguish the two figures so it's not as confusing to look at. Kind of looks like a little butterfly, you know, maybe a little dragonfly. I don't know, when you put it together, little wings, you know, go with me on it. All right. So once you have it, it just says state the coordinates of the image. So that would be all of this part. And then visually, you should be able to see that, yeah, if we fold over the line, here it is. And if the original figure, if the line runs through it, then the new figure should overlap with it as well. So we have a couple more practice with these. I'm thinking we're going to do one more, and then we'll save one for a little recap in class. So for number 2, I would like to do this one together because it's a little different. It's saying the vertices of triangle DEF are given. Draw DEF prime, the image after a reflection over the line y equals 3. So reflection over the line y equals 3. So now it's not one that we have a rule for. We're going to have to go back to visually thinking about this. So y equals 3. If I go up to 3 on the y-axis, all the points across from here are all have y values of 3. So like the point 2, 3, 4, 3, and so on. So it is a horizontal line. So let's draw that in here. And now when you draw it in, you can draw it in as a solid line, as a dotted line. Sometimes seeing that difference, I like to go back and highlight it. But if you don't have a highlighter, then I would suggest drawing it in as a dotted line. So that's the line that we're going to be reflecting over. So this is the line y equals 3. All right, if we go back to that visual to reflect over the line y equals 3, we would count the spaces when you're going perpendicular to the line. So since this is horizontal, we're going to count everything vertically. So 1 space to get to the line, 1 space past, there's D prime. For F, it's 1, 2, 3, 4 to get to the line. So 1, 2, 3, 4 past it. And then for E, 2 spaces to get to the line, 2 spaces past it. So if it's easier, plot them all first, and then you can write the answers down. So here's where they started, where they land. Let's see, D prime is at the point 3, 2. E prime is over here at 8, 1. And then F prime is at the point 6, negative 1. So even though we don't have like a hard, fast rule, we're not just negating an X or negating a Y, what you should notice is that all the X values of the original and of the image are all exactly the same. So when you're flipping over a horizontal line, the only thing changing here are the Y values. And let me actually connect the dots. So please make sure that you finish the image. Plotting the 3 points is not quite the same thing as reflecting the full triangle over. So don't forget to finish off your work there. All right, we're going to save number 3 for a little recap in class. If it's not your day to be in class, you can always join on the computer. I always make sure those Google Meets are open. So if you're not sure how to do it, join us for class to make sure that we go over it. Number 4, let's keep on moving then. Oh, number 4, just kidding. Forgot, it was only a little recap with the reflections. We are moving on to translations. So what a translation is a slide or a glide. So sometimes you'll hear the term a glide reflection. We'll talk about that later. That's a little combo move. But here, if I think about sliding a figure, I'm not flipping it over. I'm not changing the size. I'm just kind of shifting it on over to a different spot on the page. So it's saying a transformation that shifts or slides every point of the figure or graph the same distance in the same direction, right? That's kind of key. So a translation, it's going to shift, right? Every point of the figure, it's the same distance in the same direction. So when it says translate the following triangle using a translation vector V, this little vector, what a vector is, it's a directed distance. So it's a certain distance and in a certain direction. Now, if we were to get really specific about this, we could actually construct lines that would be parallel to this from the last unit. So we would draw the line, we'd swipe some arcs and so on. For today, because we don't have to get quite that specific, we're just going to estimate. So what I'd like you to do, grab a straight edge. And in this case, if I line it up, I'm going to actually just move my ruler just to the other side so that this side of it goes through point A. And I'm just going to kind of sketch in a line that looks parallel to vector V, right? So I'm going to sketch it in. Oops. And my paper moved on me a little bit. Let's see if I can fix that. Ooh, I got one of those sad erasers. Let me try that game again. I don't know if that's any better. Geez, guys, my supplies at home are a little rough over here. All right, hopefully that's enough, though, to go here. And now, come on down, slide down, and then see if you can do another line that's approximately parallel. So for today, we're just going to estimate. So you're going to kind of use your eyes, and we are eyeballing it. So draw a line that goes through each vertex of the triangle. So it looks like they are approximately parallel to each other. So you're doing the best you can, but definitely use a straight edge here. All right. So it's looking pretty decent. I'll take that. All right. Where we are going to use our compass is I'm going to use my compass to measure the length of the vector. So from pointer to pencil, I'm going to open my compass up the length of that vector, and then I'm going to copy that length from point A, from point B, and from point C. So I'm going to put my pointer on point A and copy that little length. And then I'm going to slide down. I'm going to put it on B, copy that length, put it on C, copy that length. So what you should have are 3 little arc marks. What those are where the point should have slid to. So point A is going to slide up the vector to here. So here's A prime. Point B is going to slide up the vector. Here's where B prime would go. And then point C slides along the vector, and it would hit here at C prime. All right, so now what you're going to do, connect those 3 points, and let's see how we did. Now, keep in mind, this is an estimation. This was not an exact. You have my permission to just be estimating here. So what you should have created is a triangle that is the exact same shape, same size, so essentially congruent to the first one, but it's all been shifted over a distance that's equivalent to the vector and in the direction that the vector was pointing. Right? So hopefully your freehand work is looking pretty good. You get a chance to try it one more time down at the one at the bottom. So let's slide it up and see if we can do it again. Right? So when we come down here, make sure you have a ruler hanging out by you. Right? So if I line it up, I want to use the angle that my vector is at. So what I can kind of do, if I just shimmy my ruler over just a little bit, I'm just looking for a pencil that's not attached to my compass here. All right, I'm going to slide it just a little bit. I can use this to go through point A, and then I'm going to take and use that line to kind of help guide me. So I can kind of line it up so I can get it to go through point H. And like I said, you're doing the best you can here to draw lines that look approximately parallel to one another. Because if we actually constructed it, it would take us quite a bit of time. And I don't want to spend that time right now. All right. So take a moment, eyeball your work. I'd say I'm looking pretty good here. All right, and now pick your compass back up. This vector is a different length than the last one, so adjust your compass. Go end to end. And then come on down and let's copy that length. So from point T, copy that vector length from point H, from point A, and then from point M. So we're shifting all of those points the same distance in the same direction. Plot a point, label it. So here's T prime, here's H prime, here is A prime, here is M prime. So we have a little, kind of looks like a trapezoid, but not quite. Maybe just a little quadrilateral math here. How cute. So M to H, I'm going to go H to T. Oops, I'm going to cut right through my A, but that's okay. And then M to A. And check out your work. See how you did. Do they look the same? I would say mine looks fairly reasonable. Hopefully you're like, yeah, patting yourself on the back. You're looking pretty good. Right? Is that skill something I'm going to fully test you on, being able to sketch it? No, but I want to make sure you understand what it means when they're saying move it along that vector. Right? So vector literally is a directed distance. So move it this distance in that direction. Okay. Last page. Let's talk about some rules for translations. So when we get over to this last page here, right, what we are looking at, is it's saying translations use the operations of addition and subtraction. To me, these are actually the easiest transformation that we talk about. So for x values, if we add to the x value, we are going to be shifting to the right. Whereas if we subtract from the x value, we're going to shift to the left. So these are all horizontal movements, which should make sense because the x-axis is horizontal. And then the y value, if we add to it, we're shifting up. If we subtract, we are, we are moving down. And again, that's a vertical direction, which makes sense because the y-axis is a vertical line. All right. As for the notation, there's two ways that you can do it, and you want to be familiar with both. We can say that a point xy goes to the point x plus a, y plus b, or it can be written with a capital T standing for translation, and then down in the little subscript, you put the letters a, comma, b, and then of the point xy. So you would say that you're translating point xy a distance of a, b. Makes a little more sense when you see some numbers in it, so let's take a look. When it says, how would you follow, or how would the following translate an object, right? If we have x plus 4 and then y minus 6, that's code for we're going to move the object to the right 4 units and then down 6 units. For the next one, actually, let's skip this one. Let's go down to the one with the t. For number 3, when we have a little subscript of 2, 8, that is the same as if we had had x plus 2 and then y plus 8. So they go in order. 2 goes to the x, 8 goes to the y. So that means we'd be going right 2 and then up 8. If we go all the way to the bottom, it says, is a translation a rigid motion? Well, back on the first page, we said a rigid motion is anything that doesn't change the shape or the size. And so this should not change shape or size. So yes, it is a rigid motion. And the reason for it, the pre-image and the image are the same shape and size. I'm going to say a little simpler. It does not change the shape or size. All right, those 2 that we skipped, we'll talk about those tomorrow, but I would like you to try one of them on your own, and that is number 2 right there. So I want to know, how would that translate an object? Are we going up, down, right, or left, and by how far? All right. Make sure to go answer that question right now. Thanks, guys, for watching, and I will talk to you soon.